I'll have an intro comparing the quantum Hall effect and so these guys, they have several names in the literature. So each time in the outline, I change the name so that you realize those are synonymous. So time reversal breaking topological insulator, it's also called anomalous quantum Hall effect. Time reversal topological insulator, also called quantized spin Hall effect, also known as a Z2 topological insulator. This one is also known as a Chern insulator or Z insulator. We'll see why one is Z and the other is Z2. And the plan is the core is the Kane and Melle model. Then this actually I wrote it, but I won't do it because I won't have time. But it's conceptually it's important to know that something is missing from this model, and you should check upon the stability on adding an extra term called the Rajpath spin-orbit interaction. And then the remaining of the lecture will be about understanding what is the correct topological invariant in this case, because if you don't break time reversal symmetry, then you're sure the Chern number is 0. Therefore, the topological invariant here cannot be the Chern number, but at the same time, you will see it's actually very closely related to the Chern number. And to build upon Andrei Nevidomsky's lectures of yesterday, I would like you to realize that there is a very close analogy between the Haldane model that I discussed in the previous lecture and the chiral superconductor in 2D. So the system, they may seem to be very different, but actually they have a lot in common, and they were discovered the same year. So in the first case, you have a Bloch Hamiltonian. In the simplest case, it's a 2x2 matrix parametrized by K. K lives in the first Brillouin zone. And the 2x2 space, it's actually a AB sublattice pseudospin. No real spin, and the matrix structure comes from having two atoms, two sites per unit cell. In the case of the topological superconductor, the chiral P plus IP superconductor, you don't have bands. You imagine you have electrons in the continuum. But now, because you're doing mean field theory of superconductivity, you have coupling between electron and holes. You have these anomalous pairing terms. And therefore, the natural way to write this mean field Hamiltonian into something that looks like single particle physics is the Bogolyubov-de Gennes framework, which Andrei presented. He didn't give the name, but it's the Nambu spinor representation. You also get a matrix form, 2x2, but this time it's not because of having two sites per unit cell, you are in the continuum, but it's because you have electron and holes, or if you want, you have written a Nambu spinor. So the reason for having 2x2 matrix is quite different, but then the mathematics is very similar. You have a 2x2 matrix parameterized by K. Here K is in the first Brillouin zone. Here K could be in the continuum, but in the end, you remember that when doing topological argument, Andrei had to compactify R2 into the sphere. So a little difference is K lives on the sphere, or R2 plus infinity. K here lives on the torus. So it could be slightly different, and actually it's not so easy understanding when the torus is equivalent to the sphere and when it's different as a starting space. But otherwise the mapping goes into the same place. It's the Bloch sphere in both cases, because those are 2x2 matrices. And both of these problems, they then have the same consequences. The bands carry Chern numbers. And as a consequence of Chern numbers, if you have edges, then you have gapless chiral edge modes in both cases. The only subtlety here is that here the things that moves around is a real electron. Yeah, the word is bad. It's a true electron, meaning a complex electron carries a charge. Here, the things that moves around, Majorana means it's not complex fermion, it's real fermion. It's only half of a complex fermion. So the edge modes here, they do not carry charge, and you don't have a quantized Hall effect, but you have a quantized thermal transport. But so there are differences, but you see otherwise it's very similar. So now, with my lecture and the one of Andrei, probably you have seen examples of topological insulators. topological superconductor, and also topological semi-metals. I didn't call it like this, but graphene is a topological semi-metal. Okay, so you've seen a little bit of all of the three main families of topological material, at least in the frame of band theory. Next week, you will hear about quantum spin liquids, and then you will realize that the word topology is used in the frame of, in the realm of strongly correlated electron, but in another meaning. So be aware, it will be gapped system, will also be called topological, but it will mean something different. Usually it's called topological order instead of topological insulators. There is also topology involved, but it's in a different way. As a first way to see if you are in one family or the other one, it's very easy. The family that I'm discussing with, there is always a Chern number somewhere. In the other family, it's about the degeneracy of the many-body ground state depending on the genus of the surface on which the 2D system is. Or even simpler, in the second family, the excitation, they are fractionalized. They have a fractional charge, fractional statistics, fractional spin. In my case, it's single electron-like physics, no fractionalization of the electrons. Yeah? So in one family, Chern number, in the other family, fractionalized electrons or fractionalized excitations. Okay, so let's, yes?
Are the Majorana modes in the superconductor you're talking about, are they protected in the same way against disorder as the parallel modes you discussed last time?
No, in this case, yes, I would say so. So if they are very well separated, then they are quite protected, yes. Okay, so let's move on to today's program. So I first start by recapping the 2D time reversal breaking topological insulator. I want to make the following things. The first step is that we had bands which are classified by Chern number. This is a topological invariant related to energy bands. Then you can also have topological invariant for gaps. Gaps are in between bands. Usually those two are mixed up. People say Chern number for both the gap and the bands, but the true definition is for the bands. And for the gaps, it's actually, I call it the Thouless, Komoto, Nightingale, and the Nice invariant. It's simply the sum over occupied bands of the Chern number of the bands. Okay, but this index lives in the gap, this index lives on the bands, and the physics, it's here the quantized Hall effect. So that's the quantum of conductance, and it's simply this quantum of conductance times this number. That's the main result of Thouless, Komoto, Nightingale, and the Nice. And this number, because the Chern number is an integer, it's also an integer. And the other thing which is important is that because of properties of fiber bundles where the fibers are complex Hilbert spaces, you can show that there should be no quantum Hall effect, integer quantum Hall effect in 3D because there is no Chern number in 3D. It's only 2D, actually even space dimension. There is again some second Chern number for 4D. So no quantum Hall effect in 3D. So the thing I want to talk about today is the case where now you want to keep time reversal symmetry, and the surprise is that there is still something like a topological insulator, and this was realized many years after Haldane by Kane and Miller, 2005, roughly at the same time as graphene was starting as an experimental subject. And actually the model they propose is a variation again on the tight binding model of graphene. To understand the Kane and Miller, the logics is graphene is simpler, boron nitride is a bit simpler, or is a bit more complicated. Haldane model is a little bit more complicated, and Kane-Miller is a little bit more complicated. But if you do those 4 steps, each step is very small. So here we will see that first, instead of a Z invariant, we will get a topology but related to a Z2 invariant. Z2 is a complicated way to say either trivial or non-trivial, only two families. Here there are as many families as integers. So this is the simplest group you can imagine. And it's called the Kane and Miller index, and that's the hard part actually. It's to show that there is such a topological invariant and that it only takes two values. And here the physics is not the quantized Hall effect or the anomalous quantized Hall effect. It's called the quantized spin Hall effect. So the thing which is quantized is not charge transport, but spin transport. And actually, you will see there is a twist to it. It's not really quantized. It's only in very specific models.
I'm sorry, I'm a little bit confused. So this KM index is the bands? Is the topology mirror for the bands?
No, for the gaps.
Oh, okay. But the bands will have an invariant, or?
You will see actually the bands, they have invariant, which is basically the Chern number. But when you sum like this, you obtain 0. Because when you have time reversal symmetry, each Chern number is 0. But you will see that the bands, you can still define something non-zero related to a Chern number. Okay, and here the other surprise, and this I won't enter into it, is that it also exists in 3D. So this was a big surprise. And there are these Z2 topological insulator also in 3D. Okay, another thing that I want to say in the introduction is that when you want a time reversal symmetric topological insulator, you need at least 4 bands. So if we could do it as before, we would only take 2 bands, but 2 bands it's not possible because you want an insulator, so you want a gap, so at least 2 bands. But if you have time reversal symmetry, the bands, they come in pairs. So actually, a sketch of a band structure that has time reversal invariance is something like this. Looks like mustache. The gap is here, and the special points here are points that we will encounter again. In K-space, they are called time reversal invariant momenta. For example, the center of the Brillouin zone is one such momentum, 0, 0. There, you need to have a degeneracy between the two bands. So the simplest model has 4 bands, and that's why we're going to study the simplest model possible, which is basically 2 copies of the Haldane model. So this was the how Kane and Miller started. So let's move to the second point, presentation of the model. That's the longest part. So at zeroth order, the Kane and Miller model, you can describe it like this. It's Haldane model with a certain phase on the T2 hoppings, if you remember. And in the Kane and Miller model, this is taken to be the maximally time reversal breaking phase. It's pi over 2. For spin up. So now that's the new player in the game. We have electrons with spin. And how do you get something with this time reversal invariant out of something that breaks time reversal symmetry maximally? You just add a copy of the time reversal for the other spin. So if you want, you have a Haldane model for spin up. It carries a Chern number if you're in the right phase. It breaks time reversal symmetry. And for the spin-down copy, you flip the inhomogeneous magnetic field. You remember yesterday, in the center of the Brillouin zone, the magnetic field was, let's say, up. In the, sorry, not in the Brillouin zone, in the real space hexagon. I had a region where magnetic field was pointing up, a region where magnetic field was pointing down. If you flip the sign of the phase, you flip the sign of this inhomogeneous magnetic field. Inside here, it's pointing toward the blackboard, and now in the outer regions, pointing out. Both small break time reversal symmetry, but there are images of each other under time reversal. So that's roughly the idea. And we will directly jump, instead of working out the tight binding model, we will directly jump to the low energy model. You remember? A low energy model, it maps the, instead of considering the whole Brillouin zone, we just look in the vicinity of where the gap is small, and this brings out the structure of a Dirac equation. So if I do this, I get a Hamiltonian that looks like this, and I'll explain a little bit. So this is graphene. These are the Pauli matrices for the AB sublattice. This is the set of Pauli matrices for the two valleys, K and K prime. And this spin, or pseudo-spin, it's appearing just because I'm going to the low energy effective description. It's because I'm saying that in the full Brillouin zone, there are two interesting regions, near K and near K prime. So this guy is just the plus minus that changes the chirality of the two Dirac cones. Yeah. But now we want spin. So here I need a third set of Pauli matrices that I will write as S, if you want. But here it's the identity, so it would be S0, so I don't write them. And now I want to gap, and to gap the Haldane way. So remember, the Haldane mass, it had the following property. It changes sign with the valley. So it's proportional to sigma z. That's why it's a mass in the Dirac equation. You remember this one is alpha x, this one is alpha y, and this one is the beta matrix. And now I've pulled out the, yesterday it was called Xi for the two valleys, K, K prime. Today I switch notation, it's this set of Pauli matrices, tau, that does this plus minus. So now I take this as a given positive number, and I just pulled out of this mass. You remember we had a m plus and m minus that were equal to capital M plus minus something. Capital M I set to 0, and I just keep the part really coming from the T2 second nearest neighbor hopping with the phase. In such a case, the Haldane mass is simply proportional to the valley index. So this plus minus I pull out, it's here now. So this is a model for a Haldane insulator, but now I want something for the spin. And for the spin, what I simply do in order to have this effect, I simply put SZ here. So now the sign of the mass is also changing with the spin index. So if you want, here there is an S0. I don't write the identities. Here there is an S0. There is also a tau 0. And here you get the tree set of Pauli matrices. Also, I took h bar equal to 1 and the velocity of the Dirac cone equal to 1. So that's a low energy description of a model that is basically two copies of the Haldane model. And I want you to have clear in mind the following, that if we were to work with the original tight binding Hamiltonian, we would have a matrix of size 4n times 4n, where n is the number of unit cells. It's because in each unit cell you have two sites and two spin projection. But because it's invariant under Bravais lattice translation, we use the Bloch theorem. The Bloch theorem diagonalizes the part that goes from unit cell to unit cell, and what remains is a 4 by 4 matrix. This would give 4 bands for this model, just as we need. That's what's drawn there. But in addition, we go to the low energy effective description, and then I use the notation Q. Q is only living in the neighborhood of either capital K or capital K prime. And this one becomes 8 by 8. It's 8 by 8 because now I have 3 sets of spins or pseudo-spin. Here I only have sigma, so sublattice and real spin. Here, when I do the effective description, I have sigma, S, and tau. Tau for the valley. Sublattice pseudospin, real spin, and valley isospin or valley pseudospin. Okay. So now you remember that the Haldane model was breaking time reversal symmetry. So let's check that this guy does not break time reversal symmetry. So time reversal symmetry in this frame, the transformation by time is, so you always get the fact that you need to flip Q by hand. It's an anti-unitary operator, so you need to take the complex conjugate. But here, in addition, you have a true spin, and you need to act on the spin with the time reversal operator. So you may know that the time reversal operator, it's given by Sy. So usually the time reversal operator, it's a unitary operator times complex conjugation, which you cannot write as a matrix. So this one makes it anti-unitary, this is unitary. And for spin a half, this is simply Sy. Why is it Sy? Because K, by complex conjugation, it already flips Sy, because Sy is the complex Pauli matrix, so it makes Sy star, which is minus Sy. And so to fully flip the spin, you need this guy to flip Sx and Sz. Yeah? Okay, so that's what transformation is. Is it a symmetry? If it is a symmetry, I should find my original Hamiltonian. So this part, there is no problem. That's graphene. It's time reversal invariant. So let's have a look at this part. So if I look at this part, it has the structure of a constant, mh. Actually, in the Kane and Miller context, this one is known to originate microscopically from a spin-orbit coupling, and therefore it's usually called something that reminds you it's intrinsic spin-orbit coupling. This I don't show here. You need a microscopic derivation to show that such a term is generated by spin-orbit. You can see that it has the flavor of spin-orbit because this is spin, and all the rest pertains to orbit, because this tells you whether you're close to K or K prime, and this one tells you whether you are on an A or a B sublattice. So this one has to do with orbital motion, this one has to do with spin, and it's a coupling between the two. Okay, so let's have a look at how this term transforms under time reversal symmetry. So Q to minus Q does nothing, doesn't depend on Q. Complex conjugation does nothing because these three Pauli matrices are the Pauli matrices 1 minus 1, which are diagonal, they are real. And so what is the effect of Sy? It's to, actually, yeah, here I realize I forgot something. Yes, yeah. So the operator that I wrote here for time reversal symmetry, that's the correct operator at this level of the description. But once you go to the low energy theory, because we have separated K and K prime, I need to put by hand that when I apply time reversal, I need to go from K to K prime. So I need not only to flip Sy, to flip the real spin, but I need to flip the valley. In which case the operator, it reads as follows. There is a tau x. So why is it tau x? Because tau x is the Pauli matrix, which is off diagonal, it exchanges the guys that are here, and the guys that are here are k and k prime. So in order to realize k goes to minus k, because k now I split it into a part which is either one value or the other, and a part which is the deviation, I need to flip the two of them. I need to flip the first part, which is realized by tau x, and I need to flip the second part. Yes? So now if I do this, I see what happens. Tau z becomes minus tau z because of the action of tau x. Sigma z is not acted upon, and sz is flipped by sy. And therefore, the product is unchanged. It's the same as the initial. So this term indeed respects time reversal symmetry. So it turns out that in true graphene, such a term should be present in any description because it respects every symmetry of the graphene lattice. It has inversion symmetry, I didn't show it. Time reversal symmetry also has mirror symmetry with respect to the plane of graphene. So in principle, it should be there. In other words, the correct low energy theory of graphene should be something that has a gap. But it turns out that spin-orbit coupling is so weak in carbon, because it's a small z atom, that this gap is not observed. It's too small. So the standard is to just take this number to 0. But Kane and Miller were smart enough to realize that such a term ought to be present, just on symmetry reason. And if you imagine that this term is enhanced for some reason, you go to another material, then you will see that this realizes, it opens a gap, it realizes an insulator, but an insulator which has some interesting properties, despite the fact that it doesn't break time reversal symmetry. So I just sketch the energy spectrum, if you want to have an idea. It looks like gapped graphene. So 2 Dirac cones with 2 gaps, and each band comes in 2 copies that you can think of as being spin up and spin down. So in this simple model, there is something which is a bit artificial, is that this model respects another symmetry which it should not respect in full generality, is that the Sz is actually conserved. Yes?
So the spin you're indicating there is the physical spin, and you're not considering the value index?
Here it's the physical spin. Yeah, so when it's tau z, I call it kk prime. When it's sigma z, the 2 values are A or B, and when it's the spin, it's up and down. In practice, they are all plus or minuses, but...
Right, and you're not drawing 8 bands because...
No, because here I again use the full Brillouin zone. So here is the vicinity of K, here is the vicinity of K prime. So if you want to see 8 band, I need to make a drawing just here and another drawing just here, and do not tell you that they are connected. Yeah? And then you get 8 bands. 4 bands here and 4 bands here. Okay, so this model has an artificial property, which is this. And this, at the end, we will need to argue why the properties we are going to obtain, they remain even when you don't have this conservation of Sz. So this is the part that I'm not doing, the number 3 about Rajpath spin-orbit coupling, which is another type of spin-orbit interaction that exists in the system and that breaks this conservation of Sz. So for the moment, I stick to the simplest description, and you will realize that in addition to that, it's also diagonal in tau z. So in basically among the three sets of Pauli matrices, there is only one which is fundamental or doing something. It's the sigma, because it's not diagonal. For the tau and the S, it's diagonal, and therefore I have an 8 by 8 Hamiltonian, but it's trivial to find the eigen values for the tau and S part, and therefore I obtain a Hamiltonian which is now in each block labeled by tau, taking value k prime, labeled by the spin projection, taking value up spin, down spin. And now I only have a 2 by 2 matrix. So the only matrices that remain are those. The rest are numbers. So now it's easy to obtain the energy spectrum. So the energy spectrum here, it's plus or minus function of Q. So this plus or minus turns out to be the band index. And now this is plus minus this term squared plus this term squared plus this term squared. Yeah, as usual for 2D Hamiltonians. So this is kx squared plus qy squared plus m spin orbit squared. So these are 4 gapped Dirac cones. Just redrawing this, and I get this in 4 copies. That's the plus band, the minus band, and this happens 4 times because I have it for every tau, whether plus or minus, and every s, whether plus or minus. Yeah? So this is like taking these guys and putting them on top of this. So this is a 4-fold degenerate. Okay, so now this is just the energy spectrum. Let's have a look at the topological content. So we need to look at the Hamiltonian. But you remember we have already studied the massive Dirac Hamiltonian. And we know that there is a shortcut to the Chern number when it's valid to concentrate only on the Dirac cones and we have correctly identified how many they are. Then each Dirac point, it's very easy. It contributes 1/2 to the Chern number. And the hard part is to know whether it's plus or minus. So how do you get the sign? The sign, it comes from 2 things. Product of chirality of the Dirac cone, whether it's the Dirac cone with a vortex or a Dirac cone with an anti-vortex. And then you need to know about the sign of the mass. And the sign of the mass here, this I took as a positive number. You see, this is just tau times s, because those are either plus or minus, so the sign is also just the product. So this is the contribution of 1 Dirac cone, and I need to sum over all the Dirac cones to get the value of the Chern number for the occupied bands. So I imagine my Fermi level is here, and I want to know what is the Chern number here. But I should get no surprise. Time reversal symmetry should make it 0. So this is tau square, so this is 1. It goes away. And now you see, because of this guy, I compensate the different contribution. So this is actually, it makes 1/2 plus 1/2 minus 1/2 minus 1/2. But if I want to separate the 2 spin contribution, I can look at the Chern number for up spin, and then I will find that this is 1/2 times tau and s equal to plus. So this is going to be 1. And of course, the Chern number for the down spin, it should be the compensation. So it's tau times minus 1. So this is minus 1. Again, here, no surprise. That's how we started from. You remember the Kane and Mehle model? It's the Haldane model for the spin up. with phi equal pi over 2, and I should have said also that I'm taking the inversion symmetry breaking term to 0. But basically, in the Haldane phase diagram, I'm sitting right here or right here. But you remember that this one has Chern equal 1, this one has Chern equal -1, and outside is 0. Here is the M direction that I'm not using, and I'm only playing with phi and T2. So actually, spin up is here, spin down is here, and of course the total is 0. So when you see this, you realize two things. First, there is no quantized Hall effect, because the TKNN number, the sum of the Chern number over occupied bands is 0. But still you see that there is some kind of topology inside, because actually your model contains 2 Haldane insulator inside. So we also know something actually that I did very quickly, that Andrei also did, which is the Jacobi argument. So I give you again the general framework. He did it in the context of topological superconductivity. I was planning to do it in the context of topological insulator. But the argument is always the same. You have a Dirac equation in which you have a domain wall in the mass of the Dirac, in which case, far away from the domain wall, you have gapped Dirac spectrum. And at the domain wall, because the mass vanishes, you have a mid-gap state, which is localized near the boundary. And in addition, that's the surprise, that's the reason for doing the calculation. The surprise is that this mode is chiral. So it only propagates in one direction, and the direction in which it propagates, it depends whether you're going from Chern equal 1 to Chern equal 0, or from Chern equal 0 to Chern equal 1. This flips the direction of chirality. But here, you see, we have Chern number for spin up. So if I only look at the bands for spin up, and because in the artificial model that I'm presenting now, spin up and spin down, they are completely independent. They do not talk to each other. So if I consider spin up, it's a Chern insulator. If I put an edge, between this guy and the outside, which has Chern equals 0, then I should have a chiral edge mode. So I already know that for this, I have a mode like this that carries a spin up, because that's the solution for the spin up case. On the other hand, for the spin down case, I also have a Haldane insulator which is not talking to the other guy. And therefore, if I put an edge, if I'm considering a half-infinite system and I have one edge, I should also have an edge mode. The only thing which is changing is because the Chern number in the bulk has flipped sign. It means that the edge has opposite chirality. So for the other band, the down spin, I also have a mode, but it goes down. It has the opposite chirality. Chirality is given, it means motion in one direction or the other. It depends on this slope being positive or negative. So the prediction of this artificial model in which SZ is conserved is that if I have an edge to my system with the vacuum, I should have counter-propagating edge modes living on the same edge, but they have a property which is that they are spin momentum locked. Those that move in this direction, they are spin up. Those that move in the opposite direction, they are spin down. So the prediction of Kane and Miller was the following. Imagine here, this is vacuum outside, trivial insulator. Here I have such a system, graphene with artificially strong spin-orbit coupling. I should have 2 modes. One mode goes this direction, and it has spin up. And the other mode goes with the other chirality, and it should have spin down. But of course, now you no longer have the robustness with respect to disorder. If you introduce an impurity here, and that the impurity is able to flip the spin, then backscattering is not forbidden. So what these guys realized is that here they have a system in which you have the following new idea, is that you may have topology in the sense of protected edge modes, but only provided your perturbation, they respect some symmetries. So if you forbid by hand magnetic impurities, if you only consider impurities that cannot touch the spin degree of freedom, then you will have something that will propagate without backscattering. Because if you're not able to flip the spin, you cannot reverse your direction, because direction of spin is tied to direction of motion. So that's the basic idea. I wanted to show a drawing. Do I have it here? Yeah, it's basically this one. So this drawing is actually a figure in the original Kane and Miller paper. They solved their tight binding model on a ribbon geometry, but they only represented the edge corresponding to one of the edge of the ribbon. On the other edge of the ribbon, you reverse what orange and blue are doing. So there is also, you have two churn insulator on top of each other, one for spin up, the other one for spin down. So when you reach that point, one thing that I forgot to mention is that when you have such a behavior, that inside you have band that carry churn number, but they compensate when you sum, it of course means you have no quantum Hall effect, because the sum is 0, but you could have quantized spin transport, because the difference is non-zero. So if you do this here, you get 2. And this is the reason why this effect is sometimes called quantized spin Hall effect. But there is no quantum Hall effect. So this is the simplest model that shows the effect, and it has 3 artifacts that we need to discuss. The first one is that once you go beyond this, you don't introduce this artificial symmetry. Then when you have true spin-orbit coupling, the spins, they are no longer good quantum numbers. And now you need to discuss what happens instead of spin when spin and momentum are tied together. So that's what we'll do when discussing Kramer's theorem. You also need to see whether these guys are truly robust to impurities that are not magnetic, that do not touch spin. And the other thing you need to check is whether spin transport is really quantized. Actually, it turns out that the spin transport is not truly quantized. That's why this name is not so longer used now. People prefer to call this a Z2 topological insulator, because the spin Hall effect is not really quantized. The value, it's non-zero, but you will see that its value is not quantized. It depends on the parameters of the model. So the thing that will remain is that we will see that you still have helical edge modes. This persists. And also the fact that there is some topological invariant in the bulk. We'll see how to define it. And the surprise is that the topological invariant in the bulk, it only takes 2 values and not Z values as for the churn insulator. So the robustness with respect to breaking this artificial symmetry is usually studied by introducing Rajpath spin-orbit coupling, which I'm not doing here. You add an extra term here. This extra term breaks SZ conservation law. But if this extra term is not very strong, then you see that the bands, they are deformed. You can no longer label them with the spin projection. You have a new index which is called Kramer's index, which is related to Cramer's theorem. But the bands are deformed, but as long as the gap does not close, you know that topological invariant, they should not vary. So if you find a topological invariant for the artificial model with the SZ conservation, then as long as any perturbation, even one that modifies the band Hamiltonian, if this perturbation does not close the gap, then you're sure that the topological invariant is not varying. So that's what happens with Rajpath spin-orbit coupling. By adiabatic continuity, you know that you can turn it on, but not too strong. If it becomes too strong, it closes the gap, and then you lose your topological invariant. But this I don't have time to do. It's in the notes. You can read it. So now, in the remaining time, I want first to discuss the fact that what makes this a topological insulator, or now this is known as a symmetry-protected topological insulator. In other words, a topological insulator not per se, but because you impose some symmetry conditions. So here the symmetry is a time reversal. So we first need to discuss time reversal symmetry and an important theorem in this context, which is Cramer's. So point number 3 was the Rajpath spin-orbit coupling that I'm skipping, and now comes point number 4 on time reversal symmetry and the Cramer theorem. Okay, the first thing to know about the time reversal transformation is that it's an anti-unitary operator. So this was shown long ago by Wigner. It's a bit surprising, but therefore it's usually decomposed as a unitary matrix times the complex conjugation. This is a bit of a strange operator. By definition, it takes complex conjugate of everything to its right. And the other operator is the U. Yeah. Should be like this. If that's the transformation, time reversal. If it's a symmetry, it means that it commutes with the Hamiltonian. In addition, you can show that T square can be either 1 or -1. For example, for a scalar wave function, if you imagine you have a single particle that carries no spin, if you reverse time and reverse it again, you're back to exactly the same wave function. So if you do this on a scalar wave function, you're back to yourself. That's the scalar case. But if you do it on a particle like an electron carrying a spin 1/2, when you do time reversal in one direction, you flip the spin. When you do time reversal again to come back, you flip it again. But you know that when you do a 2π rotation in real space for a spin, you actually come back to the same state, but with a pi phase. So that's the main property of the spin 1/2. You know this trick with the belt, where you show that the spin 1/2 is not like a vector. It's a vector, but with other rotation properties. So when you do it for a spin 1/2, you actually obtain minus. So spinor wave function, and here it's a scalar wave function. Okay? And so now comes Cramer's theorem. Cramer's theorem happens in the case that you have time reversal symmetry. Yeah, and I should say more generally, this happens for when the total spin is an integer, and this happens when the total spin of the system is a half integer. So when you have Cramer's theorem, it involves having time reversal symmetry and being in the case where T square equals -1. And the theorem is simply that each energy level is at least twofold degenerate. So I quickly do the proof because it's very short. So we use time reversal symmetry. Hamiltonian commutes with t, and t square equal -1. So assume that we have a level, an eigenvector with eigenenergy E, and now we want to apply t operator. So this is equal, of course, I can use the above, and this is E t psi. E is real, so time reversal does nothing on it. And now I can also use the fact that t and h, they commute. So if they commute, this is also h t psi. And now you see that this also means that t psi, the time reversal of psi, is also an eigenvector of the Hamiltonian, but with energy, same energy, E. So now imagine that this new eigenvector is actually the same as the original one, that there is no degeneracy. So I assume there is no degeneracy, which means that t psi should be proportional to psi, where c is some complex number. If it's just proportional, it means it's the same state. But now comes a contradiction. If I apply t again, this is t c psi. C is a complex number, so it gets a star. And here you obtain t psi, but this is equal to -1. And here, t psi, it's again c times psi. So this is c dagger c psi. And therefore, I obtain the fact that this positive number should be equal to -1. So this is not possible. And therefore, it means that the new state I'm producing here is truly a different eigenvector. So it's at least, the energy E is at least twofold degenerate. Okay, so we need one more step. That's very general quantum mechanics on the time reversal symmetry. But now I want to know something a little more specific. I want it in the context of the band structures. So in band structures, so for the Bloch Hamiltonian, I also want to be in the same context, having time reversal symmetry and t square equal -1. Having time reversal symmetry means that this is the time reversed transformation of the Hamiltonian, and if it's a symmetry, it means it should be equal to the original Hamiltonian. I need to flip k by hand, and the t operator, it does everything else. You remember when I discussed the three types of Hamiltonians? The original one, the full one, the tight binding one, the one after using Bloch theorem, which is a small matrix, and then the one after expanding close to k and k prime. This one has size 4n, this one 4, and this one 8. The time reversal operator, it has a different expression at each level. So you should not learn the expression by heart. You should just remember what time reversal does, and then you build the operator that does what you want. So here, for example, at this level, I need to flip k by hand. That's what I did here. At this level, I need to flip q by hand, and I need to flip the valley index by hand. Yeah? At this level, the t operator should do everything by itself. Okay, so now I want to have this property, but what does it mean? It means that for the band structure, I have the following property that I should write it like this. That an energy band, an energy at wave vector k, and here I introduce some band index, it should have a partner on another band, a flip band. If we were in the simple case where spin and orbit are not coupled, this would be the spin index. I'm flipping the spin and I'm flipping k. So that's the relation of time reversal symmetry on a bands. And you see that bands, they come in pair. That's the first information. Because of Cramer's theorem. But there is another twist to it, is that they come in pair, but the degeneracy is in K space, it may happen at two different K points. That's why I drew the model like this. You remember the four bands that looks like mustache? When I have a state here, this is this guy. When I do the time reversal, I go from K to minus K, and I will find a state at the same energy. That's the Cramer theorem, but it's not at the same K value. It's at minus K. And in addition, it has flipped index, because if you think of spin again, this is the up spin branch, and now I'm moving, and because of time reversal, I'm going to the down spin branch. Sigma minus sigma. Yeah, my notation is very bad. Here, sigma will be called Cramer's index. It's not to be confused with the sublattice Pauli matrices sigma x, sigma y, sigma z. So sigma here is called Cramer's index. It's the thing that replaces spin in case where spin is no longer a good quantum number. Okay, so now degeneracy, twofold degeneracy, but it's in K space, it's not happening at the same position in the Brillouin zone, except here, here, and here. So what are those points? Those points are points that are their own image under time reversal. So I'm asking for minus K to be equal to K, but because I'm in the Brillouin zone, it's modulo the smallest reciprocal lattice vector. So actually these points, they are known as, colloquially, they are called G over 2, or they are called time reversal invariant momenta. So on my drawing, there are 3 such points. Actually, the number of points depends on space dimension. When you are in 2D Brillouin zone, there are 4 such points. So in the 2D Brillouin zone, so I'm taking a very simple 2D Brillouin zone in the shape of a square. These 4 points are the gamma point here, the center of the Brillouin zone, 0, 0. There is this point, which is sometimes called x, this point, which is sometimes called y, and this point, which is called pi pi or m point. So under time reversal, this guy is sent to this guy, but they are equivalent by translation by reciprocal lattice vector. This guy is sent to here, but it's again equivalent to itself. This guy is sent to here, and it's equivalent to this guy. So these 4 points are special. They are special that there you're sure to find 2 energy levels at the same K position. Okay. So a band crossing at a trim is mandatory because of Cramer's theorem. So Cramer's theorem, you need time reversal symmetry, and you need that you're dealing with electrons. For example, if instead of working with real graphene, you're working with artificial graphene, where the things moving around are not electrons but bosonic particles, then you don't get this property. So it may have influences. Okay. And the last point that I need to mention in this section on time reversal symmetry. So the important point at the moment is this, that bands, they come in pairs, and that a band crossing at a trim is mandatory. And the last point I want to make is that, and I'm not doing the calculation because it's a bit long, but I'm giving the reference. It's in the book by Bernevik on page 37. the book on topological insulators and superconductors. It's that if you imagine, or I'm first writing the statement and then sketching the proof, is that a band crossing at a trim is mandatory, but in addition it's robust to any perturbation that respects time reversal symmetry. So if you imagine only impurities that are non-magnetic, then they cannot remove this degeneracy. So a band crossing at a trim is robust to any perturbation that respects time reversal symmetry. So how do you show that? Actually, you are just, maybe the statement is too general, you just check that in first order perturbation theory, you're checking that the matrix element coupling U of k, I'm in a given band in a given state, I want to see if the perturbation is able to couple to the time transformed state. And this you can show, and that's the calculation which is a bit long, you can show that this is 0 when you have this property. So now we will use these ingredients to have intuitive understanding of why the helical edge states that we have seen, those that are counter-propagating but tied to the spin direction or to the Kramer's index value, why those things, they only exist in two families. In other words, why it's only either trivial or non-trivial, but not a Z classification, but a Z2 classification. So I first want to show this from the perspective of edges. So the simplest discussion is to try to understand what happens with these helical edges. So this is part 5. And now I'm in the part where I want to show that there is some topological invariant for the edge, equivalent in the quantum Hall context to the number of chiral edge modes. I want to see that why this guy, it only takes two values. So the sketch is the following. I first consider one helical mode. So that's the case that we already discussed. I sketch the bands. I have conduction band. I have valence band. And now I want to study, I have one boundary between my system and vacuum. I know that I should have two modes like this, and that they carry opposite Kramer's index. In addition, I know that the crossing at a trim is mandatory. So here, I know that the crossing here, it occurs at the K point because of time reversal symmetry. In addition, because it occurs there, I know that this degeneracy cannot be lifted by any perturbation that respects time reversal symmetry. So I imagine I only consider perturbation that respect time reversal symmetry, and I cannot open this gap. So although I have two modes that live on the same edge and that counter-propagate, if my impurities or perturbation that respect time reversal symmetry, they cannot backscatter. And therefore, this type of transport is protected. It's as good, in principle, as a transport by a quantum Hall effect, except that I get two modes instead of only one. Okay, now let's see what happens if instead of having a Haldane model with, this is the case where churn up is 1, and churn down is -1 if you want. Now let's consider the case where I take a Haldane model, 2 copies of the Haldane model, but now one has churn up +2 and the other one has churn down -2. So now I should get 2 helical modes. What happens in this case? So I draw the bands again. So this is valence band, this is conduction band. And now I have one crossing like this, and I have another pair of helical modes. I have 2 helical modes, and the crossing, they occur at a trim. So now you see when you have 2 helical modes, it means on the same edge. If this is the edge, now I have another pair of helical modes with other Kramer's index. Now there are a lot of guys on the same edge. Could I backscatter? Could I go from here to here, for example? Because this guy may be coupled to this guy. Can I tell that just from the little arguments that I have? You see now that when you have these 2 helical modes, you see 4 crossings, 4 level crossings. But 2 level crossings are protected because they occur at a trim, and they cannot be lifted by a perturbation that breaks time reversal symmetry. But the other 2, here and here, they need not be protected. Those, there is no symmetry reason why non-magnetic impurity should not lift this degeneracy. If this happens, I open the degeneracy here, you obtain a picture like this. And now you see I've opened a gap in my system. So when you have 2 helical modes, they are not robust even to impurities that respect time reversal symmetry. So actually 2 helical modes, in terms of robustness to disorder, it's equivalent to 0 helical mode. Okay, so let's have a look at 3. So that's the main point in understanding that actually robustness is just on-off, and you cannot get as many helical modes as you want. So let's look at the case with 3 helical modes. I need to squeeze them a little bit, otherwise So now you see we get many level crossings. I think there are 9. There are 9 crossings. 3 occur at a trim. There are those where it's the Kramer's partner crossing. It's this one protected, and this one protected. This occurs at a trim. But the other ones are not protected, so now I lift all the other ones. And if you do this, it's quite magical, but okay, I should do it with another color. So this guy, so this one is protected, but not the next one, so it goes like this. This one's protected, but not the next one, so I make it an avoided crossing. I do the same here. Make it an avoided crossing. This one also an avoided crossing. Down there, so I should remove them and connect here. Avoided crossings. Probably the best thing to convince yourself is to do the drawing yourself with a good eraser. And now I still have those crossings which are not protected, so I again make them as avoided crossings. And the surprise, if you unfold everything, is that one remains there, you see? This branch and this branch. So actually, all this is gapped, but there is one out of 3 helical modes that remains ungapped. So if I redo the drawing, it's something like this. I don't care too much about those that are up there. Those are these two, but I still have one that's like this. So actually 3 is equivalent to 1. Yes, but I won't do like the time permitting. I can go up to 12, I think, if you're. Okay, so you see now if you want to define a topological invariant for the edges, it should be something like. So this topological invariant, it's something which is usually not called a topological invariant. It's just called a number of edge modes. So in the quantum Hall effect, you just count the modes. Here, it's just that you need to count them in a smart way. The smart way is that helical modes, which is a pair of counter-propagating and spin-filtered, you count as 1. And in addition, it's mode 2. So the number, or the topological invariant for the edge, it's the parity of the number of helical modes per edge. This is what replaces the simply the counting of the number of chiral edge states in the quantum Hall effect. So this is indeed, by construction, parity. Only takes 2 values, so +1, -1, or sometimes people shift it to have 0 and 1. Okay, so now let's have a look at if we are able to do something more complicated, which is to, now that we understood that the edge modes, either they are there or they are not there, and when they are there, it's only one helical mode which is robust to disorder. Are we able to understand the bulk? Is there a topological invariant for this problem? So obviously it's not the Chern number, because this one is 0. But obviously also it's strongly related to the Chern number. Because you remember in the artificial model where spin up and spin down don't talk to each other, the reason why we have something interesting is because we have 2 copies of the Haldane model below. So it's not the Chern number, but it's very strongly related. So let's see if we can make the argument. And here I'm following a paper by Raoul Roy. It's PRB 2009. There are 2, and they have almost the same title, but the argument is probably only contained in the first one. The argument is the following. There are several ways to understand why in a Chern insulator, why the Chern number is an integer. One way goes back to the first lecture on the Dirac magnetic monopole. The Dirac magnetic monopole, I told you about it in the context of electromagnetism and in real space, but you can make the same construction in reciprocal space and on the Berry connection instead of the vector potential. And you remember that the key idea was the following. In order to have a non-zero magnetic monopole charge, or in our language, in order to have a non-zero Chern number, the only way is that you need an obstruction to having a single smooth gauge for the vector potential or for the Berry connection in the whole of space. So for us, it means that the Berry connection, it should not have a single definition in the whole of Brillouin zone. And I say again what it means. This guy is computed from the UNs. You've also seen that in Andrei's lecture. And the UNs, you remember that there is a gauge choice. I call it the Berry gauge choice. That you can have a choice like this, and somebody else can have another choice, which is equally valid, but which in intermediate step is going to look quite different. Actually, if you compute the Berry connection here is going to be different. Because these guys are like the vector potential, they are gauge dependent, but when you compute the curl of it to obtain the Berry curvature, you should obtain the same result here and here. So what do I mean obstruction to finding a smooth global gauge? It means the following. When I take UN, I need to say something about how I choose my global phase. And the beloved choice is the following. If I have a 4-band structure, I have 4 components, and usually I'm happy if I can decide that the first guy is real. I'm allowed to do that. Except if the first guy vanishes somewhere in the Brillouin zone. If the first guy here that I've taken to be a real number, this real number, as I move k, all the entries here are a function of k. If I move in the Brillouin zone and somewhere I have a point where this guy vanishes, it means that my phase convention is not valid there. How do I deal with it? I do as Dirac. I say, okay, I make one patch around the point where my convention is not valid. I take first convention that I love in the remaining part. I take another convention. The other convention is like, okay, you vanish, I don't care. I take you real. Yeah? So now my convention here, I use in all of second region. But when you do this, you need to do some gluing on the boundary. You see that the boundary, it's a circle. And what do I need to glue? I need to glue the phase of the wave function. So when I study a single band, like I'm doing here, I need to glue the phase of the wave function on the boundary, because you remember on the boundary, those two vector potential, they should agree. They should agree up to they should agree for the magnetic field. So there should be a gauge transformation between the two. But the gauge transformation on the vector potential, it means a phase transformation on the wave function. If it's for a single band, the phase of the wave function, it's really a phase. It's a U1 number. So on a boundary which is S1, I need to say how to glue something which is itself is also a S1 quantity. Because U1, it's the same as S1. It's a circle. So my gluing condition, it involves mapping S1 to S1 from the boundary to the phase of the wave function. That's what Dirac did, and as a consequence of doing this, he obtains that the charge of the magnetic monopole is quantized. Why is it quantized? Because we know our homotopy groups and the fact that those mappings, they are classified by a winding number, which is a Z. So what I sketched here is a derivation of an alternative derivation of the fact that the Chern number, it has to be an integer. Okay, can we do the same for Kane and Melle? Here I did it quickly for a Chern insulator. Can we do it for the Kane and Melle model? What's the difference? So the main difference is that the thing that I need to glue now, it's no longer the phase of a wave function, but the object I'm trying to glue is a spinner. Why is it a spinner? It's a spinner because the bands, they come in pairs. So actually, you remember, again, the moustache. When I'm studying the Haldane model, I have something like this in mind. I have one band and another band. It's a 2x2 model. When I do the Kane and Melle, I have 4 bands, but the bands, they come in pairs. And therefore, when I need to project on something, here I cannot project on a single band. I need to project on a pair. So the thing I'm gluing now, it's no longer the phase of the wave function, but I'm trying to glue a spinner computed in one convention to a spinner outside computed in another convention. So I'm gluing a spinner to a spinner. So here it's not going to be S1, but it's going to be a SU2 matrix. Okay, so now SU2 matrix, it's actually the same space as S3 sphere. Topologically, it's a S3 sphere. And then I look up in the table of homotopy groups, and this is 0. For the same reason you cannot lasso a sphere, a 2 sphere, you cannot lasso a 3 sphere. Okay? So something's wrong in our argument. So the tricky part is actually the following, is that the phase is like this, but actually in our Brillouin zone, because of time reversal symmetry, the information which is contained in, I cut the Brillouin zone in 2 parts, the information which is contained in one part of the Brillouin zone, it's enough to reconstruct the information in the other part. This is because each time I know what happens at the k point, I already know what happens at the minus k point by the time reversal operator. So actually, the phase, the thing that I'm gluing, it's not really SU2, it's SU2, but in which the wave function at k and the wave function at minus k I need to identify. So here, actually, it's not SU2, it's SU2 modulo this fact that k and minus k are identified. And now if you look at this object, if you're familiar with your group theory for rotation in real space, this is not the same as a sphere. This is actually well known. It's the group of rotation in 3D space, the usual group of rotation. And you may note that the parameter space for this guy is a bit strange. It's an S3 sphere, but in which, I do it as if it was S2, in which antipodal points, they are identified. So it's only the northern hemisphere, if you want. But because everything I have down there, I have it up here. But in addition, on the equator, I only need to take half of the equator, because what I have here, I already have it here. So it's a half sphere, plus the fact that I only take half of its boundary. This is exactly the topology of this object. And this object has only 2 classes of paths. So this is indeed a Z2. And why do you have this? So I can try to sketch it. So I take half of a sphere. Actually, one way of seeing S3 is like a usual sphere, but actually filled inside a ball. So now I'm taking a ball, only half of it, and I only include half of the boundary. And I'm asking how many type of inequivalent paths there are. So I start from an arbitrary point inside. You have passes inside the sphere that go like this, and I can contract them to 0. But there is another type of path which is non-contractible, which is the fact that you can have a path that touches here, and once it touches here, it re-enters on the antipodal point here, and it closes like this. Yeah, so my drawing is very bad. You start from an arbitrary point, you touch the boundary, you re-enter at the antipodal point, and you close like this. So there is this second family of paths, which is a family of paths that uses the boundary of the system. So actually, this is a well-known result. You should find it in your lectures on the rotation group in 3D space. So that's one way in the bulk of seeing that there is a topological invariant that only takes a Z2 value. It's related to the obstruction of finding a smooth global gauge, but not for an object which is a wave function, but for an object which is a spinner. And in addition, this spinner has some special property. You see that the hard part in the explanation is understanding why you get that. Okay. So if you want more detail on that, here it's, you can find that in the paper by Raoul Roy. And yes, I want to conclude by writing explicitly an expression for this topological invariant, but this time in the bulk. The Kane and Miller index. So you remember in the case of time reversal breaking to the insulator, we have bands and Chern that carry an index which is a Chern number. And you have gaps that carry an index which is actually the sum over occupied bands of this Chern number. And both of them are integer. And one way of understanding that this is an integer, a quick way, is this obstruction to finding a global gauge that shows that there is a gluing condition that involves the first homotopy group of the sphere. So in some sense, this Z you can also understand as a winding number. There are many ways of understanding this Z. You've also seen the way Andrei showed yesterday, where you look at mapping of the sphere to the sphere, and then it looks like a wrapping number. Okay, so that's for the quantum Hall effect. Now for the time reversal symmetric topological insulator, we have bands in pairs because of Kramer's degeneracy, which means that if I take such a pair and my bands, they are labeled by a band index and a Kramer's index. So if I again look at my mustache here, it means I would take n equal 1, and then I have sigma equal 1 value and sigma equal another value. These are the two bands here. And this would be n equal 2 and sigma equal plus minus. Within a pair, the sum vanishes. But as we have seen, if you are able, and that's actually the cheat in the argument here, if you are able to define the Chern number for a single member of the pair, we know that the sum is 0, but this single value need not be 0. Do you see what's wrong with giving a Chern number to this band, for example? What's wrong with defining a Chern number for this band? Yeah, the thing which is wrong is that the band is not separated from the other band. So Chern number, they are for well-isolated bands. You should not have band contact points. So here, actually, you can do it. It's quite technical, but you split the bands, and you show that whatever the splitting of the band you do, what I will say remains true. But of course, that's the hard part of the argument. But imagine it's not an issue. I give a Chern number for this band. I give another Chern number for this band. I know that the sum to 0, but each member of this sum need not be 0. It could be 1 minus 1, 2 minus 2, 3 minus 3, etc. So then comes the obvious topological index in the bulk, introduced by Kane and Miller, but actually written like this by Raoul Roy. You simply need to sum over each pair of bands. Now n labels pairs of band. That's the pair number 1, that's the pair number 2. And you only sum the positive member in the family. So, and you take it mod 2 because you know from the correspondence with the edge, and you know from the homotopy argument that there are only 2 families. So that's one definition of the Z2 invariant. which really shows the connection to the Chern number. Actually, my understanding in hindsight is that in all the families of topological insulators that are related to non-interacting electron or weakly interacting electron, all the topology is related to Chern number, whether it's topological insulator, topological superconductor, or topological semi-metal. For the Weil semi-metal, the 3D equivalent of graphene, you can also show that the topological charge carried by the band contact, it's also a Chern number. Okay, so here you see that the Z2 invariant, sometimes it's called Z2, it's also related actually to the Chern number. And actually there is a very old theorem by Avron, Zeiler, and Simon in '83, right at the same moment as the Berry phase, that these guys, they showed that for bands, in band theory, there is only one invariant, which is the Chern number. All other invariants you are making are a combination or variation on the Chern number, a bit like this one. Okay, and I'm probably stopping here, and we're having lunch. Thank you. Maybe if you have questions. So I'm actually leaving this afternoon at 4. I'm sorry I wasn't not too much available during this school. Usually I like to attend all the lectures and to be present for the students, but we had some problem with our car. But I'm here until 4, so please feel free to annoy me or not annoy me during lunch or after lunch. Okay, thank you. Yes, so there have been experiments on both the Chern insulator and the Z2 insulator. So in Z2 insulator, it's the experiments of Molenkamp in Würzburg, and the material. The system is a 2D quantum well of HGTE, CDTE. So it's a material in which they make a quantum well like this. I think that inside it's this material, outside it's this material. This one has a higher spin orbit interaction than this one. And the effective model in 2D here, it has the same phenomenology as the Kane and Melle model. So, yeah, but I had to cut short in the lecture.